In this video, we'll talk about different methods we can use to approximate the areas under a curve. So if we have a curve we want to find the area under, say a simple graph like that, and we go ahead and chunk this up into little pieces, there's a couple of different ways we can go about finding the area, or at least approximating under this curve. First we could do is what's called a lower sum. And the idea of a lower sum is that on each little piece, I will use the smallest value of the function to give me the height of the rectangle. And so that will look something like, on this first piece, it's lowest over here, so there's my height. On the second piece, it's also lowest here, so there's a height. Third piece, fourth piece, and fifth piece, I pick the lowest value to give me the height. Now what do I know about a lower sum? Well, this is always going to be less than the actual area. See in the picture, every rectangle sits under the graph, and there's always little pieces in here that my lower sum is missing. Another approach you could take for finding the areas is called an upper sum. And you can probably guess this works the other way. I'm going to pick the largest value of the function on each piece to give me the height. So for our picture above, this now has something like, here's the first one, here's the second, third, fourth, and fifth. As you can probably see here, now this sum is always more than the area under the curve because I've added in some extra little pieces up here that are above the curve. So if I wanted to get an approximation of this area, what I could do is find a lower sum and an upper sum, and then just say my area must be somewhere between those two values, and that would give me a way to get a bound on where this area could be. A third option is what's called a midpoint sum. And this just says I want to take the height at the midpoint of each interval and use that to make my rectangles. In a picture, I'm taking the midpoint and using that height for my rectangles. So midpoint there, across to the height, midpoint across, give me the height, midpoint across, give me the height. Now in this case, I don't know if this is bigger or smaller than the actual area, because I have parts that I've added in up here and parts that I've taken out under here. So it's not obvious whether this is bigger or smaller than the actual area under the curve. In general, this is closer to the actual area than the lower upper sums, but you don't know if your sum is bigger or smaller. There's your three ways you could find these areas using this method. How do we actually go about finding these? The basic idea are, step one, break up the interval into a bunch of little pieces. And then on each piece, you want to find the appropriate height. Midpoint's usually pretty straightforward. Lower and upper might sound tricky, looking for the smallest or largest point on the subinterval. But in basically every case, the lower and upper values are at one of the endpoints. If you know what the function is doing on that interval, you can say, okay, I know the value at the right endpoint of the subinterval is going to be always bigger than the one at the left end. So the upper sum will involve me taking the right endpoint for my height, and the lower involves taking the left endpoint for my height. Let's now work this out from an example. So we have an upper, lower, midpoint sum with 4 rectangles for the area under the graph of y equals x squared plus 2 and the interval from 2 to 6. So let's draw a picture. If I have 2 to 6 with 4 rectangles, that means my rectangles all have width 1. And if we look at our picture here, we know that for a lower sum, always going to take the left-hand endpoint of each subinterval, because that's always the smallest value on each little interval. And then for upper, we're taking the right endpoints. So for lower sum, what do I get? Well, I'm going to get the function value at 2, which is 2 squared plus 2 is 6 times 1. Function value at 3 times 1. Function value at 4 times 1. 16 plus 2 is 18. Function value at 5 times 1, 27, which is 52. For an upper sum, I have the following rectangles. And so I want the function values at 3, 4, 5, and 6 instead of 2, 3, 4, and 5. So I'll get the following. I get 11 times 1 plus 18 times 1 plus 27 times 1 plus the value at 6, which is 38 times 1, which is 94. And now for midpoints, what do I want? Well, for midpoints, I want the function values at each of these points here in the middle and use those for rectangles. So I want the value at 2.5, 3.5, 4.5, and 5.5 to give you my heights. F of 2.5 is 5 halves squared is 25 over 4, plus 2 is 33 over 4. We're plugging the rest the same way. And adding these up, we get 308 over 4, which is 77. So as expected, the midpoint sum falls between the lower and upper sums, which it should do most times. And it's likely going to be a closer approximation to the area than either the upper or lower sums because it's between them. So that's the idea of approximating with rectangles, the different ways we can do that, and how to work out these calculations for these certain types of problems.